our next talk is Comparing Word Embeddings with Gensim by Parul Sethi. Parul is a third-year undergraduate student of Maths and IT at Cluster Innovation Center, University of Delhi. And you can start with
So my talk is basically on word embeddings. So I would like to first explain what word embeddings are, just to get started with basics. So as we know, the algorithms work on numbers only, but like the basic unit in language is words, the atomic unit. So how do we do processing and analysis on language? So that's where word embeddings come into play. We basically use numbers to represent the words, and they are not just random numbers. Like you can see, there's this middle cluster. These words are related, most of them, like office, market, work, officials, companies. So there are different algorithms for producing these word embeddings. So I'm basically going to talk about differences between them. So why these word embeddings are useful? Like I said, everything needs to be in numbers. So yeah, and these word vectors are basically, they can be used as an end itself for computing these, computing the exact similarity between words. Like you have a word official and then work, and they are both represented by numbers which are not random. They are produced from these algorithms. So you can directly compute their cosine similarity and know that how similar are these. So yeah, that's the direct direct use. And then they are also used as representational basis for downstream NLP tasks, like mostly these text classification, clustering, all these type of tasks. They use word embeddings only as the basic representation. These are some of the examples of word embeddings. Yeah, so like with so many embedding models coming up recently, it could be a difficult task to choose one. So should you go with the super popular word-to-vec, or is it possible that some other embedding algorithm could be more accurate for your downstream task, like classification, clustering, and all? So there are some evaluation metrics that I'm going to talk about, which could help to some extent in deciding this thing. Yeah, like this is a trivial example of the difference between these three embeddings: word rank, word2vec, and fast text. These are the results of words most similar to king. And like you can see in the word rank, the results are kind of attributes of king, or we can say the words which would be co-occurring with the word king in some general kind of corpus. And by the way, this was for text state. It is a Wikipedia dump corpus. It's the result from that corpus. And then these are the results from word2vec, and these are all the names of the king. And from the fast text, we got mixed results. So the basic difference between these two are, these represent different types of similarities. This is semantic, and this is syntactic. And what are they basically is, semantic similarities kind of like the words which could be related to the topic, and then in contrast, the syntactic similarities, you can change them in exchange with words. Like for example, we take king killed the prisoner, and we can replace the word king with all these names, like you could kill the prisoner, Canute, and all. So we can exchange these words. These are syntactic similarities. And semantic similarities, like throne, crown, monarch, and all, these are basically related to king, but we cannot exchange these words in same context. This is the difference between these two types of similarities. So yeah, I did a project on basically comparing these embeddings, and I firstly evaluated these three algorithms on similarity benchmarks, and I took two data sets, Simlex 999 and WordSim 353. They basically address these two different types of similarities. Simlex addresses the syntactic and WordSim the semantic. Now, like this is an example from this data set. And yeah, this data set is a test data. It contains word pairs with human-assigned similarity judgment. So yeah, that's the test data. And this is an example. For example, for clothes and closet, the Simlex rating is 1.96, which is very low because it addresses syntactic similarity, and these two words cannot be exchanged, like clothes and closets. And WordSim is quite high because these are very much related. In contrast, the coast and shore, they are exchangeable too, and they are obviously related. So it has a high rating in both of the test data sets. So yeah, this is the basic difference between these two test data sets. And the next test data I evaluated these three algorithms on was word analogy. It basically contains 19K analogy questions. It is like a data set with example is like, yeah, Paris, France, then Tokyo is what? Like what Paris is to France, then Tokyo is to what? Japan, obviously. So this algorithm has to predict that question word. So this is the test data. Yeah, so yeah, this is the blog I wrote about 3 months ago nearly, and these are the results I got for 3 algorithms. On the last one shows the accuracies on these data sets. These are the computational performances, like how much it shows. And this is the corpus size, 1 million and then 17 million. So you can go to this blog if you want the detailed of what algorithm performs better on which testing. Yeah, so this is basically a summary of how to get the similarity you need from different algorithms. So for the semantic similarity, which is basically the words related to it but may not be exchangeable, it can be achieved through word rank. And yeah, a special quality of word rank is that it works pretty good in small data sets too. So you can get the semantic similarity from word rank and also from word to vec, but with big window. It is a parameter related to the algorithm. So I won't be going into details right now. It would take much time. Yeah, so and then for the syntactic similarity, the word to vec with small window size, and these two other algorithms, fasttext and var embed. And actually, as a brief, window sizes basically, when these algorithms try, important thing is obviously the visualization part. It is important in every kind of data analysis task. So yeah. For my project, I used TensorBoard, like Google open sourced this visualization framework last year. So it has like different visualization techniques to your embeddings into TSV, and then just input it into the projector. This. And yeah, now coming to this. The TensorBoard basically has these two techniques for visualization. But for visualization, we obviously need to, these word embeddings are multidimensional, like 100, 200, or 3. They exist in hundreds of dimensions. But we humans are obviously restricted to 3 dimensions only. and for visualization. So we need to reduce this into 2 or 3 dimension. So these two are the very popular dimensionality reduction techniques. PCA. PCA is kind of basically tries to preserve the global structure of the data. Like, it doesn't care about the pairwise relatedness of some data points, whereas TSNE is opposite to it. It tries to address the pairwise similarity between data points. This could be, this is considered as kind of local technique, and that is a global one. Yeah, so. Okay, so yeah, so this is the TensorBoard UI. I'll just give a brief what this UI contains. This is the example data set of word2vec with 10K words, and this is basically the plot of those word embeddings in 3 dimensions. You can also choose 2 dimensions by deleting the component 3. So like if you click on a word like I did on byte, it shows you the related words in the data set, and those are the nearest points in original space. Original space means the multidimensional embedding, and that could be a little different from what we see here. I'll just isolate these data points. It's not visible. Yeah, so basically I was trying to say that the similar words could differ somewhat in lesser dimensions, obviously, because some extent of information is lost when we reduce the dimensions from hundreds to just 3. So, yeah, and you can use the choose the number of principal components for PCA, and similarly, TSNE also has some algorithm-specific parameters. These are perplexity and learning rate, and you can stop the number of iterations when it basically stops updating. Like you can see, it is at somewhat stable configuration. And yeah, this blog about how to use TSNE is a must-read before using this technique, because TSNE can have some drawbacks, and you need to care about some specific points, and you should definitely read this blog before using it. So the last part is about the relation of word frequency and model performance. It is not important that if your algorithm works, gives a good performance on some test data, then it is going to perform well for your queries, all kind of queries that we want to do on that corpus. It depends on the frequency of the question word. Like this is the frequency. It basically means these are the rare words, and these are the highly frequent words at the last in the corpus we are training on. So yeah, this is the graphy. This is the accuracy on analogy test data, which I described earlier. So we observed that all the 3 models perform poorly on rare words and highly frequent words. and gave an optimized performance on the middle frequent words. And yeah, the next conclusion was that for semantic analogies, word rank performed the best for all range of frequency, and for syntactic analogies, the above one, that is syntactic, fast text performed the best for all the ranges of frequency, and this is basically total semantic plus syntactic. Here you see that fast text is performing the best over the range of frequency, but that is not quite conclusive, because the test data contains the total number of semantic analogies around, I guess, 5K, and total number of syntactic around 10K. So that's the basic reason. So this total analogy can't be that conclusive in that case. Yeah, that's it. These are the references for the blog, which has the details of this experiment of the 3 embeddings blog and the associated Jupyter notebook for producing all the results. And yeah, this is just an example of how we can achieve different similarities with using different window size in Word2Vec. So, any questions? Yeah. Graph. Yeah, I did that contribution, this contribution under Gensim only. So. Yeah, it was a part of student incubator program, which is organized by, like, Gensim is sponsored by a private company, Rare Technologies, whose founder is the creator of the Gensim only. So he has this student program under his company. So I participated in that and worked on this project, which was basically to contribute to Gensim only.
Great. Thank you.